Assalamualaikum and hi, my name is Siti Nursyada binti Ilyas. Today we want to present about inspection methods for 5 conventional NDT techniques. This is our team members. First, Sarah Emily. Second, Awara Hana. Third, Nurina Ziha. 4, Nurina Jiha. 5, Aimi Umara. And I, Siti Nursyada binti Ilyas. In this presentation, we will explore 5 essential non-destructive testing techniques. These include UT, eddy current, radiography, magnetic particle, and penetrate testing.
Firstly, what is ultrasonic testing? Ultrasonic testing is a non-destructive testing method used to inspect the internal structure of materials. It utilizes high-frequency sound wave, typically between 0.5 to 20 MHz, operating similarly to medical ultrasound, but it applied to engineering materials like metals, welds, and composite. The main objective of UT is to detect internal flaws and measure material thickness accurately without causing any damage. So we move to the equipment overview. The first one is UT flow detector. UT flow detector generates electrical pulse and display the signal as scan graph. For transducer, which is probe, it convert electrical energy into sound wave. It have two beam, which is straight and angle beam. For straight beam is for thickness and delamination, and for angle beam is for weld inspection. The third one is couplant. It eliminates air gaps between the probe and the material surface to allow sound transmission. Next, we are moving to the step-by-step inspection procedure. Step 1. For the surface preparation, you have to clean the test surface from rust, scale, or paint for proper contact. Step 2. For calibration, we have to calibrate the UT machine using standard reference block. For example, V1 or V2 blocks for accuracy. Step 3. Apply couplant. We have to spread a thin, even layer of gel over the inspection area. And the last one is scanning. We have to move the probe smoothly in a consistent grid pattern while monitoring the screen. So for the key safety precaution, the first one is personal protective equipment, which is PPE, safety shoes, safety glass, and glove. Second one is chemical safety. We have to ensure that the couplant is non-toxic, skin safe, and non-corrosive to the material. Lastly, for environment safety, we have to follow the standard precaution for working at high confined space or near heavy machinery. For example, pipelines and shipyards. Next, we move to how to read a scan display. There is two signal, which is normal signal and defect signal. For normal signal, it shows an initial pass, this is start, and a backward echo at the bottom of the material. Second one is defect. It is a new peak or echo appears between the initial pulse and backward echo. What it means, the sound bounce back early off a flaw, which is crack, void, or porosity. The position of the peak indicates the exact depth of the defect. So, for conclusion, ultrasonic testing is an invaluable NDT method that ensures structural integrity by detecting deep internal flaws and measuring thickness from just one accessible site. Its high accuracy and locating and sizing defects make it critical for preventing catastrophic failure. Ultimately, UT plays a vital role in maintaining safety standards across major industry, including aerospace, pipelines, and construction.
So now I will explain about eddy current testing or ECT. Eddy current testing is a non-destructive testing method used to detect surface and near surface defect in conductive materials. It works best under electromagnetic inductions. The process is simple, which is an alternating current flows through a probe coil, creating a magnetic field. These magnetic fields induce eddy current in the test materials. If there is a crack or defect, the flow of this current change, and the instrument detect the damage. So on the right side is the equipment overview. The eddy current instrument generate the AC current and display the inspection results. The probe or test coil create the magnetic field and detect the defect. The calibration block is used to set up and verify the equipment before testing. Finally, the test specimen is the material being inspected. Next, I will explain the eddy current testing inspection procedure. So firstly, prepare the equipment and test the specimens. Then, clean the specimen surface to ensure accurate results. After that, connect the probe to the instrument and calibrate the equipment using a calibration blocks. Once the setup is complete, place the probe on the specimen and scan the inspection area. While scanning, observe any signal change as this may indicate defect. Finally, record and analyze the results. It is also important to follow safety precautions. Always calibrate the equipment before testings. Check that the probe and cables are in good conditions. Avoid using the damaged equipment, then follow the laboratory safety rules and handle the specimen carefully. So if you're following these steps, it will help ensure accurate inspection and save the operations. After the inspection is complete, the result needs to be interpreted. For our defect-free materials, the eddy current flow normally through the materials and the signal displays on the instrument remains stable. However, if there are defects such as a crack or discontinuity, the flow of eddy current is disturbed. This causes a change in the coil's impedance, which appears as a signal change on the instruments. By analyzing this signal change, inspectors can be identify the presence and location of defect in the materials. Finally, let's look at the advantage and limitation of eddy current testing. Some key advantages are that it provides fast inspections, which does not require a couplants, has high sensitivity to surface cracks, is non-destructive and can be automated for efficient testings. However, there are some limitations. Eddy current testing only works on conductive materials, which has limit penetration depth, and the condition on the surface can affect the accuracy on the results. So, for the conclusions, eddy current testing is a fast and reliable non-destructive testing method that uses electromagnetic induction to detect surface and near-surface defect. Because of its speed and effectiveness, it is widely used in industries such as aerospace, automotive, and manufacturing to ensure product quality and safety.
For the next topic is radiographic testing. What is radiographic testing? Radiographic testing is an entity method used to inspect the inside of materials for hidden flaws using high energy radiation. It uses short wavelength electromagnetic radiation, either X-ray or gamma ray, to penetrate deep into the materials. It is like an X-ray you get at a hospital, but instead of looking for broken bones, you are looking for voids inside of engineering structures. For equipment overview of radiographic testing, the first we have the radiation source. We either use X-ray generator or a radioactive isotope source like iridium-192 or cobalt-60. And then we have image quality indicator, a small wire or hole type gauge placed on the part to prove our radiographic image has good sensitivity and clarity. And then we have the detector film, a photographic film coated on both sides with a radiation sensitive silver halide emulsion to capture the internal image of our structure. And then lastly we have collimators. Collimators is a LED device placed over gamma sources to safely direct the radiation path only towards the area of interest. For the step-by-step inspection procedure for radiographic testing, the first step is the setup. We have to place the test object directly between the radiation source and the film to secure an IQI onto the front surface of the object. Second is the exposure. We have to turn on the X-ray machine or safely deploy the radioactive source capsule using a remote control. The radiation will pass through the object and expose the film, creating a hidden lantern image. And then the third step is the development. Take the film into a dark room and process it through a chemical sequence, which is a developer to show the image stop bath to end the reaction, and fixer to make it permanent. The last step is washing and drying. We have to wash the film thoroughly in running water to clear away chemicals, then dry it completely before interpretation. We have to remember the safety precaution, which is, unlike under NDT method, radiation cannot be seen, felt or heard, and it can actively damage living cells. So we have to minimize exposure time, maximize distance from the source, and always use dense shielding material like lead or concrete. Radiographers must always monitor the area using portable radiation detection safety meters to measure live dose rates. How are the defects detected? First, by reading the shadowgraph, the developed film is looked at on a light box as a shadow picture. Second one is spotting flaws. Thicker or denser solid metal stops more radiation, making those areas look lighter on the film. And then, lastly, the contrast difference. If there is an internal defect, like a hollow gas pore or a crack, less material is there to block the radiation. So, more photons hit the film in that spot, revealing the flaw as a distinct dark line or spot against the lighter background. So, why is this method is important? Radiography is one of the most critical NDT methods because it is provide an unarguable permanent visual record of a component's internal health. By verifying internal structure without destroying the parts, radiography keeps complex industries like aerospace, oil and gas, and manufacturing running safely every day. That's all.
What is magnetic particle testing? Magnetic particle testing, or MT, is a non-destructive testing method used to detect surface or near-surface defects in ferromagnetic materials such as steel and iron. The inspection works by magnetizing the material and applying magnetic particle to the surface. If a defect is present, the particle will gather around it and make it visible. For the main equipment included in this testing, the first one is magnetic yoke. It produces a magnetic field within the test object to help reveal the defects. The second one is magnetic particles, fine iron particles that gather at the defect location to make them more visible. The third one is a UV lamp, used with fluorescent particles to improve visibility in dark environments. And the fourth one is a cleaner, to remove the dirt, oil, rust, and contaminants before the inspection. And the last one is PPE, also known as personal protective equipment. It protects the inspectors from chemicals, particles, and electrical hazard. Next, we move on to the step-by-step inspection procedure. For the first step is to clean the surface, to remove the oil, grease, paint, or dirt. For the second step is to magnetize the component by applying a magnetic field using the magnetic yoke. For the third step is apply the magnetic particle by spray or dust the magnetic particle evenly over the inspection area. For the fourth step is to observe the indications, like look for the particle accumulation. For the fifth step is to record the result. And the last step is to demagnetize and clean the component. Let's look at the safety precautions of this testing. To ensure safety during the testing, inspectors should wear a PPE, check the electrical equipment before use, avoid excessive UV exposure, and work in a well-ventilated area. So let's look at the results. There are three most common results that can happen. For the first one is particle accumulation. This is where the magnetic particles gather around the magnetic flux leakage occur, and the common defects detected is cracks, laps, non-metallic inclusions, and surgations. For the second one is defect indication. The visible particle pattern may indicate cracks or discontinuous. This means that they may or may not be a defect in the area. And the last one is no indication. Even particle distribution suggests no detectable defects. This means the component is all good. There's no defect on the component. So there are several advantages of this magnetic testing. For the first one, it is highly sensitive, it is easy to use, fast inspection, clear indication, and minimal pre-cleaning. As for the limitations, the first one, it only works for ferromatic materials. The second one is limited depth detection. The third one is operator dependent. The fourth one is surface preparation required. And the fifth one is the demagnetization is needed. So in conclusion, magnetic particle testing is fast and effective non-destructive testing method used to detect surface and near-surface defect in ferromatic materials. It provides a clear defect indications, helping ensure the quality, safety, and reliability of engineering components. That's all.
What is liquid penetrate testing? Liquid penetrate testing, or LPT, is a highly cost-effective method used to detect cracks or flaws open to the material surface, relying entirely on the physical principle of the capillary action. The process follows 6 simple steps. First, clean the surface. Next, apply the penetrant dye and let it dwell. Wash away the excess surface dye, apply a white developer to draw out the trapped liquid. Inspect the visible indication and finally post-clean the part. For on-site inspection or field work, technicians use a portable 3-can aerosol kit. This includes a solvent cleaner, the penetrant dye, which can be a bright visible red, or a glowing fluorescent dye, and a spray on a white developer. For large-scale manufacturing, automated stationary line with a large deep tank and drying oven are used. The inspection stage also requires specialized equipment such as UVA LED lamps for fluorescent dyes and TAM calibration panels to verify the testing chemicals are working correctly. Liquid penetrate testing is a high effective method used to find surface broken cracks and flaws. The entire process relies on capillary action, which is a liquid natural ability to seep into tight space. First step, the surface must be completely clean because any dirt or oil will block the crack and keep the dye out. Next, we apply the liquid penetrant dye and let it sit for a specific dwell time, usually 5 to 10 minutes, so it can soak deep into the flaws. Next is removing the excess penetrant from the surface. Our goal is to leave the dye strictly inside the cracks. Remember to wipe the surface with a damp cloth instead of spraying cleaner directly. Then, we spray a thin layer of a white developer. This powder acts like a sponge, drawing the trapped dye back out to the surface area. Next, we inspect the part. The trapped dye blinks out against the white background, making fine cracks clearly visible under a strong white light, or a UV lamp if you are using fluorescent dye. Finally, cleaning, post-cleaning, where we wash away all chemical residues to protect the material from corrosion. As you can see here, they have 2 types of penetrant. First, visible dye penetrant, and second, fluorescent penetrant.
Next, I will explain the key safety precautions and interpretation of results in liquid penetrant testing. First, proper chemical handling and surface smearing prevention are important because penetrant, developer, and the cleaning solvent may contain the volatile substance, while excessive blending or machining can seal the crack openings and affect the inspection accuracy. Second, the surface condition must be clean and free from the contaminant to ensure the penetrant can enter any surface defect. Third, inspection should be conducted within the recommended temperature limits of 4 degrees Celsius to 52 degrees Celsius, as temperature outside this range may reduce the effectiveness of the testing materials. Inspection lighting is also essential. Visible dye inspections require adequate white light, while the fluorescent dye inspection requires the ultraviolet light in a dark environment. For result interpretation, liquid penetrant testing provides a surface visual map that shows the location and pattern of defect on the material surface. The developer produces a bleed out effect by drawing the penetrant trap inside defect back to the surface, making the indication easier to observe. The method also offers the high contrast visibility either through the visible dyes or fluorescent dyes, which improve the defect detection. Different indication shape represent the different type of defects. Continuous line usually indicate the crack. Round spot may indicate the porosity or pinhole, and intermittent lines may suggest the partially closed defect. Therefore, proper interpretation of this indication is important for accurate defect identification and evaluation. In conclusion, liquid penetrant testing is highly effective non-destructive testing method used to detect the surface breaking defects in a wide range of engineering materials and components. One of its greatest advantages is its adaptability. It can be used on a metallic, non-metallic, magnetic, and non-magnetic materials, making it suitable for the various industry and application. Liquid penetrant testing is also the cost-effective and portable because it requires relatively simple equipment and can be performed both in the lab and in the field inspection. This makes the practical choice for the routine quality control and maintenance activities. Another important advantage is its ability to provide the high sensitivity for detecting surface defect. Even a very small cracks, pinhole, and the other surface discontinuities can be detected effectively, helping to prevent the failures and improve the product reliability. However, this method is limited to defects that are open to the surface and cannot detect internal flaws hidden beneath the material. For this reason, it is often used together with other non-destructive testing methods when a more comprehensive evaluation is required. Overall, liquid penetrant testing remains one of the most widely used inspection techniques because of its simplicity, reliability, versatility, and effectiveness. It played an important role in ensuring the product quality, structural integrity, and the safety in the industries such as aerospace, automotive, manufacturing, power generation, and the construction. Thank you for your attention.